Hello again. We're getting into a section where we're looking at electric current and how it can create magnetic fields and other neat phenomena. And I thought we'd do a review on electric current in case you haven't thought about that in a little while. So, when scientists were first studying electricity, they found that you could rub certain materials together, like silk and glass, or wood and wax, or wood and glass, and silk and amber. And in some cases, those two objects would pick up electric charges, one from the other. And in some cases, the objects would pick up positive charges. And in some cases, they would pick up negative charges. And things got interesting if you had two objects with opposite charges nearby, because opposite charges attract each other. If you had these objects and they were kind of close, they would try to jump together and stick like magnets. And if they did stick, if they did come into contact, their charges would suddenly disappear. They would be acting like magnets and trying to get towards each other, and as soon as they touched, suddenly they were like a couple of rocks and there was no more attraction force or anything, and their electrical properties just vanished until you got out your wax or your silk or whatever and charged them up again. So there was something in these objects that could be built up and then dissipated by touching them. And that was what came to be known as electric charge. Now, if you have a couple of charged objects, you can connect them with a metal wire or something else that conducts electricity. And what would happen then is these objects would still discharge, but it happened gradually. This object's positive charge would go 10, 9, 8, 7, 6 until it got down to zero. This negative object might start at minus 10 and go minus 9, minus 8, minus 7, minus 6 until it got to zero, and only then would the electrical flow stop. It was like a battery dying, where it starts out fully charged and then the charge gets weaker and weaker until it's finally gone and these objects aren't electrical anymore. So Benjamin Franklin, one of the first people to study this, came up with an interpretation where he said, all right, what if there's some kind of positive electrical fluid? They called it fluid because it flowed. And the positive side is full of that. He said, what if positive charge means there's some positive thing in here that can flow? And a positive charge means you have lots of it, and a negative charge means you don't have it. Well, this positive charge would be attracted to the negative side because opposite charges, and it would start to flow out of the plus side and over into the minus side. As that happens, the positive side, which was a great big tank of pluses, starts running out of pluses. So the positives might start out with 10, and then you get 9, 8, 7, 6. So you're running out of pluses because they're flowing out into the other side of the apparatus. That would explain why this side loses its charge. And this side, which might have started out as a minus 10, starts to get more positive as pluses flow into it. So it goes minus 9, minus 8, minus 7, until it gets to zero. That interpretation, where there's positive charges flowing, is still in use today. And you can easily find videos and articles where people say that it's wrong and we shouldn't use it, but the pros do use it and there's really nothing wrong with it. That interpretation said that there is positive charge flow, which goes out of the positive side and into the negative side. That interpretation is what we call conventional current. Now, there's another way to explain what we're seeing here. Where we say instead of pluses flowing out of the plus side, we know that there are particles called electrons and we know that they're negative. Another way to think of this is that when you have a negative charge, that means this side is full of electrons, which are negative. So the negative terminal is a big tank of minuses, And those minuses would look out and say, oh, a positively charged object, we're attracted to that, let's flow towards it. And in that case, you get negative charges flowing out of the minus side into the plus side. And there again, if you think of this as a big tank of minuses, they're now flowing out. So this goes minus 10, minus 9, minus 8, minus 7. It gets more and more positive because the negative charges are leaving. This side, which used to be a plus 10, goes 9, 8, 7, 6. It gets pulled down because negative charge is flowing into it. All the same stuff happens, but now we interpret it as negative charge flow, mainly electrons. And negative charges go out of the negative side and into the positive side. If you're doing this kind of flow, we generally call this electron current. Both can work, and you actually should be able to work with either one of these, because we can give you problems where we say, like, draw an arrow on this circuit to indicate the direction of the electron flow. In which case you should say, in this case you'd say the electron flow is from right to left, out of the negative terminal and into the positive. We could just as easily say, draw an arrow on this diagram showing the conventional current flow, and then you would say, conventional current is out of the positive and into the negative. They both work. You should be able to switch gears at will between those two things. Electron current is maybe slightly preferable just because we know that in most electric currents, in most electronic devices, the charge carriers really are electrons. And so this is the direction the particles are really flowing. But pretty much every kind of analysis you're ever going to do, you can just as easily use conventional current flow and it will work fine. The reason, by the way, that we talk primarily about electrons flowing, or we say that that's the real direction of electron flow, is that in most objects, or in most materials, the positive charges are in the nuclei of atoms, which are relatively fixed in place, especially if you're in a solid. The protons cannot move. They are stuck in the nuclei of their atoms and can't really go anywhere. Even if there's a voltage applied that makes them want to move, they can't because they're locked in place, connected to their neighbors by intermolecular forces. But the electrons in conductive materials are free to move. The electrons will be all around this area. If they're conduction electrons, they're scattered all around these atoms, and they can go running off. If you apply a voltage to this material, all the electrons can go stampeding off to the left or right or up or down, whichever way a voltage pulls them. They will leave their parent atoms behind, and the electrons will go and respond to that voltage. So in a circuit like this, where you've got a voltage or an electrical potential, it's the electrons that will go moving, and the positives generally stay put. That's why we generally prefer to talk about electron current. But just to say it one last time, both of these can work. I encourage you to be comfortable with both.